So thanks for coming out to the Atlanta Robotics Monthly Meetup. This is our inaugural meetup. We hope to do these monthly, and our goal is to expand the field of robotics in Atlanta by highlighting people who are in the industry, startups, hobbyists, people who do it for fun and all over. So if you don't mind, I'd like to go around the room and just, if you quickly just give your name and how you're involved with robotics. And I'll start. I'm CBQ. I'm with a startup called Greensy, and we build software for autonomous robotic lawnmowers. And I've been a big fan of robotics for a long time. Skip you? All right.
Eric. I've just started learning software development, and I'm interested in robotics.
Awesome.
I'm Michael, and I look at a different set of robotics, more robotic process automation.
RPA.
And very happy to be here.
Paul, my background's in signal processing, so I'm very attracted to robotics and getting into it.
I'm Adrian, and I'm in the paper industry and e-commerce, and I'm just interested in learning more about robotics.
I'm Mauricio. I'm an engineer in the construction industry, and I can see the industry moving forward into robotics, so I'm looking to learn more.
I'm Mark. I'm in the entertainment industry. We use robots to basically mill foam, cut scenery, and I represent a couple of different softwares, Robot Master, which is a plugin for Mastercam, and RoboDK, which is kind of an all-around software, but I also developed a plugin for Mastercam for RoboDK as well.
Cool.
I'm Linda, and I'm in the healthcare industry, and I've recently started to learn about robotics and machine learning.
I'm Philip. I'm in the architecture manufacturing industry, and really I just kind of came to hear different people's approaches to like robotics implementations and kind of different mindsets and kind of like how we can like cross-platform those kinds of things.
I'm Will. I'm a recent Georgia Tech graduate, and I'm the first employee of Greensy.
And where are you going in January?
In January, I'm going to work for Amazon Robotics.
Oh, nice.
Yeah.
And so I have the honor of introducing our guest speaker tonight. We have Barry, or Barrett Clark. You go by Barry, yeah?
Barry.
So Barry is the CTO of SoftWear Automation, which you'll hear a little bit about, and it's very clever spelling. So if you've looked them up, they do, I won't steal his thunder, but they're doing a lot of really cool work here in Atlanta, Georgia. Now you're not from here though.
I'm not.
Where you, and I'm sure you'll get there. Look at that, from Louisville, Kentucky. So real happy to have him. He's just going to talk a little bit. Feel free to ask questions. He's going to leave a little bit of questions at the end. Some quick housekeeping. If you need to get up, go to the restroom. They're right outside. And then our next meetup is in November, and we are looking for a speaker. We have some line on a couple, but I'd love introductions. We can handle one or two. Usually one is what we need. We're probably going to cancel the December one. It's just too close to the holidays. And we have some other cool ones lined up. January, February, we're probably going to be hosting it at different locations. That one may be at the Georgia Tech Robo Jackets. They've got a unique lab where they want to host us, either for January or February. So looking forward to that one. But if you have ideas for speakers, we're also going to be at the Decatur Makers Space, and that may be January or February as well. It could be November. Lou may move it up to then. But keep on the mailing list on the Atlanta Meetup. That's the best way to find out. And with further ado, Barry, take it away. Thank you.
So my name is Barry Clark, I'm co-CTO of SoftWear Automation. So I want to talk a little bit about trends in robotics and kind of how they apply to automated sewing. I'm actually going to talk about these things kind of in reverse order. So I'm originally from Louisville, Kentucky. I've been interested in taking things apart my whole life. I recently finished my PhD in optimal control of robots. Particularly legged robots. And for the last 5 years, I've been working for SoftWear. So I kind of was basically the second full-time employee. So SoftWear Automation is a automated sewing startup. So we were founded by a professor, Professor Emeritus out of Georgia Tech. And the central thesis was that you needed computer vision to fully automate sewing. So there have been a lot of attempts in the past, and they'd all really failed because of kind of the lack of computer vision. So we were originally funded by DARPA in 2012, So DARPA was really interested. You might think, DARPA is a defense agency. Why is DARPA interested in sewing? Well, there's this thing called the Berry Amendment, ironically, which dictates that all military uniforms have to be manufactured in the United States. So they're very interested in filling kind of this labor gap that exists to actually be able to manufacture military uniforms. After that funding ran out, we actually raised several rounds of funding starting in 2014. And our goal really is to build IP around building blocks for automated sewing. So sewing is really interesting because it's really dictated by the good you're making. So the way in which you sew a pair of pants is much different than the way you sew a pair of, a shirt is much different than the way you would sew a pillowcase. And so it's really hard to find a one-size-fits-all solution. So we're really interested in building the building blocks to be able to automate different things with the knowledge that they're not really going to look the same. There's a lot of reasons that you want to automate sewing. One of the biggest is actually you wouldn't think it to begin with, but sewing is the third largest polluting industry in the world. So when you think about the fact that the majority of cotton is grown in the United States and then it's all shipped overseas to be sewn, and then it's usually shipped back to the United States because we're the largest consumer country, that's one good reason. And then there's many, many more other than that. I mean, there's a lot of waste in the garment industry, so you actually, in order to produce enough clothes and kind of be able to make use of the logistics as they are today, clothes are basically on a 6-month cycle, so they have to decide what to order and purchase 6 months ahead of the season in which they'll actually be purchased. And kind of the list for reasons why you might want to automate goes on and on. So these, sorry, I missed that order. So the state of the art in robotics. So I have some better videos, but these are two kind of very interesting collaborative robots. On the right, we have Baxter, which is made by Rethink Robotics, which actually just went out of business. Yeah. And on the left, we have a UR robot, which is a very popular type of collaborative robot. And they're not doing anything super crazy right now, but you can see, I mean, they're able to see things on their own. They're able to manipulate things kind of like humans might. And so, this slide basically shows, robots can do some things that are pretty interesting. They're pretty smart. So the state of the art in robotics is pretty high, I would say. And you kind of compare that to the state of the art in sewing. On the top left, I have just a room full of people, right? So that basically is the state of the art in sewing right now. Industries throw people at the problem. So there's not a whole, if you go to a sewing factory, the only robots you're going to see are in the cutting portion, where they're actually making kind of the raw pieces of material that get sewn together. In the bottom right hand, I have maybe a less facetious video of hard automation. So this is what they call a pocket setter. So it's putting a pocket onto a jean leg. And so this really is sort of the most advanced automation that you would see frequently in a sewing factory. And this hasn't been innovated upon since like 1980, right? So this has been around for a really long time. It's very expensive. It can only do one thing. It does do that one thing pretty well. But at the end of the day, most companies would choose just to throw a couple people at the problem rather than to invest in that piece of equipment. And so our innovation really is to use high-speed computer vision combined with precise fabric manipulation to try and build these flexible machines that can do a variety of things. And so kind of in order to do that, we try to take advantage of the fact that robots are really good at certain things. So on the right, we have an Israeli company called Mobileye. So they make the majority of computer vision systems for self-driving cars. And then on the left, we have a PCB assembly board, which is made by Essemtech. But these machines are able to do much more precise movements than a human in a much less amount of time. And so the idea here is that robots are really good at doing things fast, right? So if you look at the frame rate of your average computer vision system as compared to a human, it's taking a lot more images than the human eye, right? It's able to process them much more quickly. A lot of the drawbacks right now are in its ability to really tell what things are, right? But it can take all that information in and make something of it kind of much faster than a human can. Speed also goes to the actual manipulation, right? So robots are able to move at much faster than a human can in a much more precise motion. And then we look at learning, right? So that's one of the things that robots are getting much better at. Kind of historically, humans have been much better at learning than robots, right? And that's kind of what's differentiated us. But today's world, computers are able to learn certain things really well, right? So if you look at predictive analytics for failure, right? That's something that a machine can do much better than a human can do. So we're trying to take advantage of these things that robots do well. So now I'm going to talk about kind of 3 separate areas of interesting technology that kind of helps software automation do what we do. So we have computer vision, navigation, and then learning and optimization. So computer vision, right? We're really looking at how do you make sense of information, information that you can see. So here we have a camera that's attached to an unmanned air vehicle. And basically what happens is this UAV has a really simple algorithm. It wants to go straight. And the issue is that there's actually things in front of it, right? And so this very simple vision system can actually detect and then create a control signal that moves the plane out of the way. And then here we actually have, this is a simulation of a Atlas robot. Used to be called Petman, but this is Boston Dynamics robot. This is actually showing kind of in real time how its computer vision system can look at the environment and tell what's going on. And then again, it's turning that into a decision tree that allows it to move throughout the environment. And both of these things are very similar to the way in which we're doing things. So when the fabric distorts, right, we're using computer vision to actually tell us how it moves and kind of how to change the control signal to actually sew the perfect piece every time. And we have navigation. So here we have some quadcopters, right? So they're really popular these days. But the average off-the-shelf quadcopter can't quite fly like this. And so what's actually happening here is they're using kind of advanced control and navigation to modify this path on the fly, right? So a human is not controlling this, the quadcopter is actually controlling itself. And so it's able to kind of identify where it is and very quickly, so thousands of times a second, actually kind of modify how it's flying in order to navigate through kind of a changing environment. And so again, this kind of relates directly to how we do sewing, right? So this is a much more interesting video than how we do it. But the idea is that nothing is static. You can't assume that your environment is not changing. So by taking kind of information from the surrounding environment, we're modifying how the robot does things. And then learning. There's a lot of different machine learning things out there, a lot of different videos. So I actually have 2 slightly different learning videos. So here we have a professor from Columbia named Hod Lipson, but he actually builds robots that learn how to locomote by themselves, right? So he kind of gives them some structure and they're actually unable to move on their own, right? And then kind of through this process of optimization and learning, they're actually able to learn how to move forward in this very kind of natural, albeit maybe creepy way, right? And then maybe a slightly more applicable example is that this robot is actually, they teach a particular task. So in this particular case, it's how to stack all these blocks up. And then as it goes forward, it actually learns how to do that better and faster, regardless of where the blocks are, right? So this is basically kind of a teach-repeat exercise with the robot. But then on top of that, they build in this learning exercise where it not only does the task, but it continually does the task better and better, right? And that's, I mean, that kind of in all robotics is turning out to be very popular, right? Because you're generating all this data as you go forward, and you know, if you're not trying to get better, then you're not really using that information, right? So, kind of a short presentation. Again, my name is Barry Clark. It was a little bit about emerging trends in robotics as well as software automation. And then this is a blooper reel from the DARPA Robotics Challenge.
Nice.
So this took place in 2015, I believe. And the idea here is that even though robots can do a lot of things really cool, this was, you know, a group of the smartest people, smartest roboticists in the world. They still had a lot of trouble making these impressive machines walk straight. So I would argue legged locomotion is one of those things that we still don't have a great idea of how to make robots do.
Wow, that's a great reel.
So that was kind of fast, but any questions?
Lots. Thank you, that was great. Yeah, thank you. What kind of technology are you using in the Sobots?
So we use a lot of stuff. So everything's written in C++ and Python. We use a lot of Linux. We only use Linux. We use a industrial Ethernet protocol called EtherCAT. So it allows for kind of like 1 millisecond update times. So that's really nice because that basically means you can get 1,000 times a second you can send information to and get information back from your robot. So that allows you to make decisions a lot faster.
That's cool.
Yeah.
And you said you are using some ROS?
We use ROS, right? So we use ROS as a framework for a lot of what we do. A lot of the kind of lower level stuff is just written in C, but then that's kind of hooked into ROS, right, for the higher level communication. ROS is robotic operating system, and it has a lot of really built out features already. It's very popular in the academic community, and it makes getting started with certain types of robotics really easy.
I feel bad watching these poor bots.
Do you also do the mechanical part, or?
So like my background's in mechanical engineering. I focus mostly on software and controls. But yeah, we build soup to nuts robots. So we do all the hardware, all the software. We try to do it strategically, right? So it doesn't always make sense to buy or to build, right? There's a lot of stuff that you can get off the shelf.
So for example, for the robots that were failing there, do they work together with different mechanical groups and software groups?
Yeah, so you could go, so for this particular competition, you could go either way. I don't exactly remember how it worked, but I think the majority of the participants, particularly the participants that did well, used Boston Dynamics Atlas as their test bed, and then they deployed their own software on that robot. I think that was probably before they were bought by Google, but maybe not. And then you could also build your own. So some of the ones that look a little different were labs or companies that decided to try and build their own hardware. And I think that's actually the team that won the overall prize was from South Korea, I believe. They built their own. But the majority of the other teams that did well used the Boston Dynamics robot.
So you mentioned that to solve the sewing problem, you needed a lot of computer vision. How do you exactly use CV to tackle that problem?
So we kind of have like a three-pronged approach, right? So in 2D, right, we do a lot of feature detection near the needle, right? So you're looking at kind of all the different aspects of the fabric and tracking it as it goes through. And you can use things like Kalman filters or other different types of ways of combining information, right, to basically close the loop, right? So you have some sort of open loop path that you're trying to follow. So you know, if you're trying to, the easiest example, you want to follow a straight line, right? But your sewing machine and your robot have different speeds, right? And so the fabric begins to wrinkle, right? And so you want to actually slow down or speed something up, right? You can't just keep going that way. So having the camera near the needle, you can see what's going on and you can adjust speeds so that you go through, right? And so that's one way, right? Then we can use 3D vision, right? So we can actually look at kind of a point cloud map of what's going on and use that information to manipulate the fabric further, right? So the cameras are great, right? Because they give you can take one image and do multiple things with it, right? And so instead of having a specialized sensor for every single thing you want to do, yeah, so there's a lot of different things we do, but the general idea is that you're trying to get a position based upon what the camera sees and then change what the robot's doing.
So you rely exclusively on vision, pretty much?
That's exclusively strong, but we use a lot of vision, right? And that's really kind of what we consider our core competency. But I mean, when you're trying to build, so right now we announced probably 8 months ago like the first completely automated t-shirt line. And so that's going to do somewhere between like 10 and 15 sewing operations. And in order to be able to do that well, we're going to use a lot of classic automation, right? So really the idea is that it's this, 50-yard black box, and on one side you put in kind of raw material, and on the other side like a t-shirt pops out, right? So there's a lot of different types of optical sensors and pneumatic solenoids and all that stuff. But in terms of like the core IP and what's actually happening near the sew head, that's a lot of computer vision.
What's the frame rate on it?
So I mean, obviously that depends on what your resolution is. So the update rates that we get for our kind of high-speed feedback, we do between 100 and 150.
Oh wow.
So that's all on a CPU, right? When I first started, we were doing a lot of stuff on custom FPGA boards, where we would do like 800 frames a second at 200 by 200.
That's the resolution, 200 by 200?
Yeah.
Oh wow.
So you're looking really, really close, right?
Right, so it's just
And
tiny resolution, but very fast.
But yeah.
Cool.
But that, I don't know, custom hardware is a pain, right? It's really, really hard to scale, particularly kind of when you're not selling thousands of things, to have custom hardware. So we did some things to our algorithms that allowed us to offload them to CPU, GPU, and get away with like, between 150 and 300 frames a second. Right now where we're at is putting on a GPU doesn't really speed it up that much, but what it allows you to do is you can run like 10 cameras on one GPU versus like 2 cameras on one CPU.
And that was the other question I had, was if you're using off-the-shelf SBC or
Yep.
you're building your own.
Everything right now is off the shelf. Yeah.
Cool. Very cool.
You mentioned that you began with rounds of funding in 2014. Where do you see the business heading? Do you see increased demand for the?
Yeah, definitely. I mean, you always know there's increased demand when people try to copy you, right? So there's definitely, so it's getting harder and harder to find labor, right? And when we first started, that was definitely true in the United States. So the number was like, in the last 30 years, they're gone from like 5 million to 150,000 sewers in the United States, and the average age of the 150,000 was like 58. And so what's happening is, even if you go overseas, I mean, China, right, is having a hell of a time finding labor. It's something like 70% of sewers don't come back after their first year, right?
Wow.
It's not a good job. I mean, at the end of the day, right? It's you're in a 95-degree factory. It's not what people want to be doing anywhere. So I think that, you know, automating sewing is going to happen no matter what. People are trying to do it on their own, right? So some of the larger factories that we've dealt with are trying to use, you know, off-the-shelf components like a 6-axis arm, like some sort of Cognex camera, and actually piece it together, right? But that will only get you so far, right? That works on kind of low-quality goods. There's some amount of synchronization and kind of control algorithm that you need, that we have kind of the secret sauce for, that you can't get just trying to do this kind of in 4 weeks.
So have you started taking some of the design process and augmenting it with wearable technology?
So you're trying to like integrate wearables?
Like monitors into some of the t-shirts that you're putting together and things like that?
We've definitely talked to people about it. At the end of the day, right now, the problems in manufacturing we're trying to solve are hard enough that that would just be a distraction, unfortunately. But that is like, those are the fun problems, right? That hopefully in a couple of years we'll be able to focus on those.
You could imagine too that this would open that up, because you don't have a lot of waste. You know, like when there's like a really expensive fabric and you've got machines that can use every bit and not like a miscut, just toss it out.
Yeah.
What's the impact to quality, to your point, versus if you had a human doing it?
So machines are always like more consistent than humans, right? And so on average, what we see is if our robot has a problem in the field, then everything has a problem. And if our robot is sewing well, then everything's good, right? And there's not as many sort of like one-off failures, right? Because their neighbor's not talking to them or whatever, right? So I mean, we certainly still have problems sewing certain things, but when we're capable of deploying something in the field, it's very consistent, right?
What is the productivity like? How many t-shirts, or how is it scaling right now?
I mean, that's a good question. So it doesn't necessarily scale well for everything, right?
The simplest part.
So right now, I mean, our U.S. customers can get a payback between 9 and 12 months, right? So the ROI is really high. It doesn't. I mean, obviously, like, it still doesn't scale that well overseas, right? But the more complicated the product is, the better the ROI. Yeah.
Cool. Any more questions? Awesome. Well, thank you very much. Great. So